Good day everyone, my name is Chang Wei Shun. My matrix number is 205677. Today I'm going to talk about the fluid properties and also dimensional analysis and modeling. So for fluid properties, first of all we have to know what is fluid, and we will talk about the introduction to fluid properties, Newtonian and non-Newtonian fluids, surface stretch and elastic modulus, and also the compressivity of fluid and vapor pressure. So what is fluid? In physics, a fluid is a substance that continually deforms under an applied shear stress or external force. Fluids are a phase of metal, including liquids, gases, and plasmas. They are substances with zero shear modulus, or in simple terms, substances which cannot resist any shear force applied to them. Fluids display properties such as resisting permanent deformation, resisting only relative rates of deformation in a dissipative frictional manner, and the ability to flow. So for the introduction to fluid properties, first can be either liquids or gases, and they can be categorized by density, specific weight, specific gravity, specific volume, pressure, surface tension, and also viscosity. So for the first one, density. So the definition for density is the amount of mass per unit volume of a substance. So as you can see, the formula is ρ equals to m over v, where v is the volume of a substance having a mass m. So the unit in SI system is kg over meter cubic. So for specific weight with the symbol of gamma, the definition is the amount of weight per unit volume of a substance. Formula is gamma equals to W over V. V is the volume of substance having a weight W, and the unit in SI system is Newton over meter cubic. For specific gravity, Hg, the definition is the ratio of the density of a substance to the density of water at 4 degrees Celsius, where the density of water at 4 degrees Celsius is actually 1000 kg over meter cubic. And specific gravity can be said as the ratio of the specific weight of a substance to specific weight of water at 4 degrees Celsius also, where the specific weight of water at 4 degrees Celsius is 9.81 kilonewton over meter cubic. So as you can see, this is the follower. This is the formula, and we will next. So now I would like to talk about the relation between density and specific weight. So first of all, formula of specific weight, we know that is gamma equal to W over V. So by multiplying the numerator and denominator of this equation by G, where G we get gamma equals to Wg over Vg. So M actually is equal to W over G, therefore we get gamma equals to Mg over V. And since density equals to M over V, right, so therefore we get gamma equals to rho G. So next is the specific volume. The definition is the number of cubic meters occupied by 1 kilogram of matter. The ratio specific volume can also be said as the ratio of a material's volume to its mass, which is the same as the reciprocal of its density. So they have three formulas. The first one is the small v equals to volume over mass. The second one is the V equals to 1 over rho, which is density, and this equation is actually used for liquids and solids. And the third one is V equals to RT over P, is used for ideal gases or real gases. The unit for specific volume is meter cubic over kg. So next is pressure. The definition of pressure is the amount of force exerted on a unit area of substance. The formula is P equals to F over A, where it's force over area, and the unit is Pascal. And pressure actually they follow the Pascal's laws. The first one is pressure acts uniformly in all directions on a small volume of fluid, as you can see on the picture at the right hand side, which shows the arrows, the direction of fluid pressure on boundaries. And the second law is in a fluid confined by solid boundaries, pressure acts perpendicular to the boundaries. Okay. Next. So now we would like to talk about the surface tension of fluid. Surface tension can be said as the tendency of liquid surfaces to shrink into the minimum surface area possible. So the real definition is the property of the surface of a liquid that allows it to resist an external force due to cohesive nature of its molecules. So how surface tension of fluid can be occurred? So surface tension is due to the cohesive forces between liquid molecules. The water molecules beneath the water surface are attracted to each other and to those at the surface. The stronger cohesion between the water molecules as opposed to the attraction of the water molecules to the air make it difficult to move an object through the surface. Surface tension can be measured as the work per unit area required to move lower molecules to the surface of the liquid. The formula is surface tension equals to work over area, and the unit is Newton over meter in SI system. Examples of phenomena due to surface tension is walking on water for the small insects such as the water strider can walk on water because their weight is not enough to penetrate the surface. And the second one is why bubbles are round. The surface tension of water provides the necessary wall tension for the formation of bubbles with water. The tendency to minimize the wall's tension pulls the bubbles into spherical shapes. So now I want to talk about viscosity. There are two types of viscosity, which is dynamic viscosity and also kinematic viscosity. For dynamic viscosity, first of all, we have to know shear stress, which is tau, the force required to slide one unit area a layer of a substance over another. The unit is usually Newton over meter square or Pascal in SI system. And next, we have to know also the velocity gradient, which is same with shear rate and is the measure of the velocity change. Uh, Actually, shear stress is directly proportional to the velocity gradient, as you can see the formula here. So when you see the graph here, you can see that this is the uh, viscosity and is directly proportional to the velocity gradient here. Dynamic viscosity of a fluid can be said as the measure of the resistance to flow exerted by a fluid. So the formula is viscosity equals to the shear stress over velocity gradient. There are few units for dynamic viscosity. There are three in SI system, which is n dot s over m square, or pas dot s, or kg over m dot s. For kinematic viscosity, there are two definitions. The first one is the ratio between the dynamic viscosity and the density of the fluid. The second definition is the measure of a fluid's internal resistance to flow under gravitational force. The formula is V equals to dynamic viscosity over density. The unit is meter square over S in SI. Yes. So I would like to talk about Newtonian fluids. Newtonian fluids can be characterized by viscosity that is independent on shear rate. The example of Newtonian fluids are water or oil. This fluid display a linear relation between shear stress and shear rate, which you can refer to the graph here. And the only parameter needed to describe the model is the slope of the shear stress versus shear rate relationship. By definition, this slope corresponds to the viscosity. So another example for Newtonian fluids are gasoline, alcohol, and kerosene. So for non-Newtonian fluids, the definition is they are the fluids that do not follow the Newton's law of viscosity, where they are dependent on shear stress and shear rate. This is the main difference from Newtonian fluids. There are two classifications of non-Newtonian fluids, which the first one is time-dependent fluids. Viscosity at any shear rate doesn't vary with time. And the second one is time-dependent fluids, which viscosity changes with time. So you can see the graph here. So when you see the steeper the slope, so the higher the apparent velocity. So let's look at time-independent fluids. There are three types of time-independent fluids, which are pseudoplastic, dilatant fluids, and also Bingham fluids. The example for pseudoplastic is blood plasma, molten polyethylene, lattices, syrups, adhesives, and inks. And for dilatant fluids, the examples are titanium dioxide, which is a material in paint, and starch in water. Cornstarch is ethylene glycol. And for Bingham fluids, they are chocolate, toothpaste, and mayonnaise. Now let's look at the graph for pseudoplastic and also dilatant fluids. The plot of shear stress versus velocity gradient, or we call shear rate here, we can see here, lies above the straight line for Newtonian fluids. The curve begins to steep, indicating higher apparent velocity. The slope decreases with increasing velocity gradient. So actually when we combine these four graphs together, we'll get a graph like something like this. Yeah, something like this. So for the dilatant fluids, the plot of shear stress versus shear rate here. So we can see the curve of dilatant fluids lies below the straight line. If we have straight line here, it lies below the straight line for the Newtonian fluids. So the curve begins with a low slope, indicating a low apparent viscosity. The slope then increases with increasing velocity gradient here. The next one is time-dependent fluid. The examples are printers, inks, jellies, crude oils at low temperatures, and flour dough. So apparent velocity carries with time as well as with velocity gradient and temperature, referring to time-dependent fluid. So there are two types of time-dependent fluid. The first one is thesotrophic fluids. It is a fluid that exhibits trophic, whereby the apparent viscosity decreases with time as shear rate remains constant. The other one is rheopatic fluid, a fluid that exhibits rhapexy, whereby the viscosity increases with time. So the behavior of time-dependent fluids, in this case, the temperature is held at constant. The vertical axis is apparent viscosity here, while the horizontal axis is time. So when shear rate changes at here probably, the apparent viscosity for rheopatic fluids will increase, and for the apparent viscosity for thesotrophic fluids will decrease. Now I would like to talk about the surface stress and elastic modulus. An elastic modulus is a quantity that measures an object of substance resistant to being deformed elastically when stress is applied to it. So it's defined based on Hooke's law. The formula is modulus equals to stress over strain. So Young modulus is defined as the ratio between tensile stress to tensile strain, and the unit is Newton over meter square. So a very important thing is a measure of materials modulus of elasticity is not a measure of strength. Next is compressibility. Compressibility is defined as the measure of the change in volume resulting from the external pressure applied to the surface of an object. The fractional volume change of an object is the ratio of the change in volume to the initial volume. The ratio may be estimated from this formula here. So where C is the compressibility of the object, and the change of P is the applied external pressure. The minus sign in C for C here needed to assure that an increase in the applied external pressure will result in decrease in the volume of the object. So similarly, a decrease in the applied external pressure will result in increase in the volume of the object. Compressibility. Actually, gases are more compressible than liquids and solids. Why? Because most of the volume of gas is composed of the large amounts of empty space between the gas particles, and a liquid is almost incompressible fluid. It conforms the shape of the container and retains a constant volume independent of pressure. Now I would like to talk about vapor pressure. The definition is a measure of the tendency of a material to change into the gases of vapor state, and it increases with temperature. The temperature at which the vapor pressure at the surface of a liquid becomes equal to the pressure exerted by the surroundings is called the boiling point of the liquid. So how it works? How vapor pressure works? When a solid or liquid evaporates to gas in a closed container, the molecules cannot escape. Some of the gas molecules will eventually strike the condensed phase and condense back into it. So you can see from the picture here. So when the rate of condensation of the gas becomes equal to the rate of evaporation of the liquid or solid, the amount of gas liquid and solid no longer changes. So the gas is can be said to in equilibrium with the liquid of solid. So now we want to talk about the dimensional analysis and modeling. For this topic, we will touch on dimensions and dimensional homogeneity, dimensional analysis and similarity, dimensional terms, the method of repeating variables, and the Buckingham Pi theorem. So first of all, we have to know what is dimension. Generally, dimension is a measure of a physical quantity without numerical values. So there are few primary dimensions which we can call it as basic dimensions also. There are time, length, mass, temperature, current, and amount of light, amount of matter. So non-primary dimensions can be calculated by multiplying or dividing by other dimensions. The example is like volume, velocity, acceleration, weight, and other else. So this shows the table for the primary dimension with their symbols and units. So for mass, we uh, use m, length is L, time is T, temperature is T, capital letter T, and electric current we call it I, amount of light we call C, amount of matter we use N. So these are the SI units for this basic dimension. So next we will proceed to dimensional homogeneity. In a dimensionally homogeneous relationship for a physical process, each term will have the same dimensions. Law of dimensional homogeneity states that every additive term in an equation must have the same direction, and calculations are only valid when the units are also homogeneous in each additive terms. So now I have a simple example of dimensional homogeneity. So we will use the Bernoulli equations. So this is the Bernoulli equations. And first of all, we have to verify that each additive term in Bernoulli equation has the same dimensions. So the second, we have to determine the dimension of constant C. Okay, now let's do it together. The solution for A is we have to write all the terms in their primary dimensions. So for the first term is P, pressure. Pressure equals to force over area. So equals to mass times length over time times length over 1 over length square. So this is the final dimension we'll get. And the second one is 1 over 2 rho v squared. So it's mass over volume times length over time square. So when we times all this, we'll get same dimension as the first one, pressure also. And the last term is the rho g jack. So it's actually mass volume times length over time square times length. So we'll get the same dimension as the both uh, pressure and the second term also. So from here we can uh, determine that all the dimension for all the terms are the same. So that's the dimension for the C constant, which is m over t squared L. So next, we'll talk about the dimensional analysis. Dimensional analysis actually is a mathematical technique used to predict physical parameters that influence the flow in fluid mechanics, heat transfer in thermodynamics, and so on. The purposes of introduction of dimensional analysis, there are three. So the first one, we want to obtain scaling laws so that the prototype performance can be predicted from model performance. The second one, we want to generate non-dimensional parameters that helps in the design of experiments and help in reporting experimental results. And the third one, we want to predict trends in the relationships between parameters. So for similarity, there are three conditions to complete similarity between a prototype and a model. So the first one is geometrical similarity, the second one is kinematic similarity, and the last one is dynamic similarity. So for the geometrical similarity, the model must be same as the prototype but maybe scaled by some constant scale factor. So as you can see from this picture, you see the prototype is much bigger than model, right? But actually they are very identical in shape. They are just different in size. This is what we call as constant scale factor. So geometrical similarity exists between model and prototype when both of them are identical in shape, like what I said, but only different in size. The ratio in all the corresponding linear dimension is equal. The ratio of dimension of model and corresponding dimension of prototype is called scale ratio. So geometrical scale ratio can be less than, equal to, or greater than 1. So this is the formula we can refer to. So next is kinematic similarity. Kinematic similarity is said exists between model and prototype if the ratio of velocity and acceleration corresponding points in the model and at the corresponding points at the prototype are the same. So we can refer to these two formulas for velocity and acceleration. Kinematic scale ratio can be either less than, equal to, or greater than 1. Next, we will go to dynamic similarity. Dynamic similarity can be achieved when all forces in the model flow scale a constant factor to corresponding forces in the prototype flow. So this is the formula. Actually, nearly the same as kinematic similarity. And then similarity, their dimensionless numbers should be the same for both model and prototype. So you can refer to this picture, and the upper one actually is for the acceleration and velocity. We can refer this picture for the kinematic similarity, and the lower part we can refer to dynamic similarity. Now let's proceed to dimensional terms. The first terms we have to know is non-dimensionalization. The definition is the partial or full removal of physical dimensions from an equation involving physical quantities by a suitable substitution of variables. This technique can simplify and parameterize problems where measure units are involved. It's closely related to dimensional analysis actually. The dimensionless numbers are ratios that indicate the importance of a term of the equation with respect to the reference term. In particular, if the equation has been divided by the convective term, these are the common variables and dimensional groups in fluid mechanics from here that we have to know. So as we can see, there are Reynolds numbers, fluid numbers, Euler numbers, Cauchy numbers, Mach numbers, Strobel numbers, variant numbers. So this is the how we can get all the numbers, and these are the application. So this is the dimensional groups that the basic dimensional groups that we have to know. Next. Finally, I will touch the method of repeating variables and Buckingham Pi theorem. Repeating variables are any set of variables which cannot form a dimensionless group by themselves. Like diameter, velocity, and height cannot be arranged in any way such that their dimensions would cancel, so they form a set of repeating variables. These are the steps to be followed in performing a dimensional analysis using the method of repeating variables. The first one is we have to list all the variables that are involved in the problem. Step 2, we have to express each of the variables in terms of basic dimensions. Step 3, determine the required number of pi terms. Step 4, select a number of repeating variables where the number required is equal to the number of reference dimensions, usually the same as the number of basic dimensions. Step 5. Form the pi term by multiplying one of the non-repeating variables by the product of repeating variables, each raised to an exponent that will make the combination dimensionless. Step 6. Repeat step 5 for each of the remaining non-repeating variables. Step 7. Check all the resulting pi terms to make sure they are dimensionless. And step 8. Express the final form as a relationship among the pi terms and think about what it means. Now I would like to talk about Buckingham's pi theorem. So Buckingham's pi theorem states that if there are n variables in a problem and these variables contain primary dimensions, for example MLT, the equation relating all the variables will have n to m dimensionless groups. Buckingham referred to these groups as pi groups. The final equation obtained is in the form of this, right? So these are the basic formula that we can get for the Buckingham's pi theorem, where R equals to number of non-dimensional variables and equals to number of physical dimension involved, and M is the primary dimensions. So let's have a simple example for the Buckingham pi theorems. So the head loss in a horizontal pipe in turbulent flow is related to the pressure drop, the change of pressure, and is a measure of the resistance to flow in the pipe. It depends on the diameter, the viscosity and density, the length of the pipe, the velocity of the flow, and the surface roughness. So next, we will do it one by one. So step 1, we have to list the dimension of these parameters, right? So for diameter, the dimension is capital L, velocity of the flow is LT, power of -1, density is ml power of -3. For the pressure drop is the ml -1, T -2. Viscosity is ml power of -1, T power of -1, and the length of pipe is L, and roughness is dimensionless. So steps 2, we have to choose. So we choose D, V, and density as repeating variables. So our first dimensional group involves pressure drop expressed in the form like this, where D to the power of A, V to the power of B, density to the power of C, and also pressure drop to the power of D. So we have to write down the dimensions for each of the terms above, right? So from this equation, we can get the relations where 0 equals to C plus D, 0 equals to -P minus 2D, 0 equals to A plus B, minus 3C, and minus D. So step 3, we know the relation already, so we have to equating coefficient of MTL respectively. So writing them in terms of D. So from the relation we get just now, we will get the C equals to -D, B equals to -2D. So when we insert into this equation, so actually we'll get A equal to 0, and we will resubstituting to the formula that we formed just now. So this is the formula we get, and so this is dimensionless, and the pi one we get is pressure drop over density times the velocity square. So for step 4, we repeat the process with viscosity to get second dimensionless group. So we did what we did before this. So just insert the viscosity in the formula like this. So same with what we did just now. So we'll get equating coefficients. We'll get 0 equals to c plus d, 0 equals to negative b minus d, 0 equals to a plus b, minus 3c minus d. So at the end we will get c equals to negative d, b equals to negative d, a equals to negative d. So we start substituting these values to the formula above. So we get the pi 2, which equal to viscosity over density times diameter times velocity. So step 5, we have to recognize the Reynolds numbers written upside down. So actually it's pi 2, so we just written it in upside down form. So step 6, we will determine next dimensionless group. Next dimensionless group will involve L, which is length, with dimension L. However, one of the repeated variable is diameter D. So actually the ratio of the two is already dimensionless. So we can straight away get pi 3 equals to L over D. For step 7, actually roughness is already dimensionless, so we straight away get pi 4 equals to roughness. So step 8, we will rewrite this relation in relation between the groups or in full. So this is the form that I show in the first slide of Buckingham's pi theorem. So we just insert what we already got for pi 1, pi 2, pi 3, and pi 4 into this form. So that's all for this example for Bucking pi theorems. And thank you for listening. Thank you.